I wanted to take some time to go over a topic that we might not get to discuss in class, but it's a pretty interesting application of induced current, and that is electric generators. How do we make electricity? So we're going to look at like a super simple situation, but just to give you an idea of how we can generate electricity, and it uses Faraday's law. So the general idea is sort of shown here. What we have is a magnetic field, so you can see that it's set up north to south. So a pretty uniform magnetic field. And then there's this wire loop. Now the wire loop is actually made so that there's some sort of external force that makes it rotate. And I'll talk a little bit about that in a minute. But something makes that wire loop rotate in the magnetic field. Now, the dimensions of the loop are that it's L units high. This is a picture actually from our text. W/2 is half of this width, so that could be confusing, but let's just remember that it has a width and a length, and so that's how big it is. Now, it's going to rotate. You can see right here, it has an angular velocity of omega, and that is going to influence what the angle is that the loop area makes with the magnetic field. And so now you can start to see maybe what we're going to talk about with respect to Faraday's law. So in this scenario, the magnetic flux, of course, is B times A times the cosine of theta. Theta, of course, is the angle between the area of the loop and the magnetic field. Our angle theta is constantly changing because of the fact that the loop is rotating. In fact, I said it rotates with a constant angular speed of omega. And so we can rewrite the angle as omega times t. That's simply the angle equals the angular velocity times the time. So this is the magnetic flux through the loop. Now, Faraday's law says that the EMF is minus the change in that magnetic flux over time. And so what would we get? We get minus, and then we get B times A, and then we get the derivative of cosine is sine. What's minus sine? And then we have to take the derivative of the angle with respect to time. And so we're going to get B A omega sine omega t. What is the area? The area is the length times the width times omega sine omega t. It's an unfortunate mixing of omega and w's. Hopefully you can see that there's a definite difference. This is the width of the loop. This is the angular velocity of the loop, how fast it's rotating. But in any case, you can see that this is what the EMF is that's generated in this because of this rotating loop. We're going to look at a graph in a moment, but you can see that all this could be thought of as E naught, which is the amplitude. And that's sort of like the peak, because this is going to vary just like a sine function and vary with time with a maximum amplitude of E naught. Keep in mind that if I put an N in here, if I have N loops, then this is going to be N E naught sine omega t, where of course E naught is going to be the BLW times omega. And so now you can start to see, hopefully you get the sense of why it's important to have many loops, because you basically magnify the effect by having a stack of loops instead of just a single loop. You're going to get much more bang for your buck, if you will. So what does this end up looking like? Here's a picture, and I think we can still sort of see enough that I don't have to erase too much. So again, you see the picture here, and I'm going to get rid of this in a minute so we can see closer, but I want to just call your attention to this graph. And so this is the graph of the voltage that is induced because of the rotating loop. You can see that the voltage actually varies with time. Sometimes it's positive, sometimes it's negative. If you think about the use of Ohm's law in this situation, you can see that the current is also going to have this sinusoidal dependence. That is, the current is not going to be a constant value. Instead, it's going to be what we call AC current, which stands for alternating current, which means it's a current that, varies with time. It's not a simple, just constant like 3 amps, but it's varying maybe between positive 3 amps and negative 3 amps. This is the kind of current that we're getting out of the wall socket. If we plug any of our appliances or anything into the socket, we're going to be getting alternating current. Let's see, what else did I want to talk about? So you can also see, of course, that the period, this is a graph of the EMF versus time. So one period would constitute going through one complete oscillation, and that would be equal to 2 pi over omega. So the period, or therefore also remember that frequency is 1 over the period, is going to be really determined by how quickly that loop is rotating in the magnetic field, which we could have control over. And so it turns out that we always expect our alternating current to have a particular frequency. So typically the frequency that's used in the US is either 50 or 60 hertz, although sometimes you can have two-phase current, so it might be a little bit of a combination of the two. And, but this is something universal, and we have to sort of have control over the current that's going to be coming out of our walls, because our devices are made to work with that particular type of alternating current. I wanted to sort of mention a little bit, exactly what is it that makes this rotate. So we're talking about right here, remember we said that there's some external force that's making the loop rotate in the magnetic field. That rotation of the loop is extremely important because of the fact that that is how we're generating an induced EMF and therefore a current, which we could use. At a very, very simple level of how a power plant would work, a power plant is trying to generate electricity for the surrounding communities. And at a very simple level, this is sort of the methods that's being used. How do we get that turning? What is causing it? And the answer is that we're basically burning fuel to create either a steam turbine, so to turn it using the steam, or if you're using water power like hydroelectric, you could literally be using the power of the water to turn a turbine, which is going to cause this rotation and generate the electric power. Now, of course, that is an oversimplification, but it does give you a very basic idea of, what's going on and or how we're creating electricity. And so that is why at this point, why do we have coal-burning power plants or gas-burning power plants? In the end, we're just really trying to create some sort of method to turn our turbines so that we can generate the electricity that we need. And so if we could figure out something better, then we wouldn't have to use those fossil fuels to do that. I want you to also notice here in this picture that there's these two rings that are attached here, and in a sense each one of those is in contact with either end of the loop, so that's how we sort of then, get the electricity out of here and allow it to travel somewhere else. And then this is going to be related to something else that we do. When it's set up like this, the same sort of polarity is always associated with the same terminal here. So as it turns, it's literally going to go through the positive and negative values. We do have a way for us to, actually create more of what we would call direct current. And so I want to just make this a little more clear so you can see everything. This is where we're trying to generate more of direct current and not have it be, go between positive and negative. And what we have here is the loop, instead of being solid, and there's one loop that's attached to a positive terminal and one loop that is attached to a negative terminal, like we saw in the last picture, we have a split ring. And what happens is that as the loop is rotating, what's going to happen is the terminals will be kind of switch which end of the loop they're attached to in a precise way, so that the EMF that is always coming out always has some positive value. Now you still have sort of the oscillation, you still goes up and down, it's not solid. But as your book talks about, we could have several of these rings, and if they're just slightly offset so that we create a lot of these curves that are just slightly out of phase with each other, when they all add together, we can get a relatively constant output of EMF, which will also allow us to have a constant current coming out. And then we can have more of what we would think of as a direct current. And so, literally having just that split ring that connects to the rest of the circuit can allow us to go from the totally oscillating, well, I'm not going to go back right now because I can't figure it out, from the totally oscillating picture to something that's more of a direct current. Now, so in all these scenarios, what we're talking about is we're talking about a generator. So the idea is, if we want to sort of grossly simplify it, we use an external force to cause our loop to rotate in a magnetic field. We'll go back to our original picture. We're going to use some external force to make this loop turn, and in turn it generates electricity. Another thing that we can do is we can basically do this backwards, and then it's called a motor. If we send current through this loop and we place it in the magnetic field, remember that then a loop carrying current in a magnetic field will feel a net torque. So if we actually did the opposite, instead of turning the loop to create electricity and current, we could send current through the loop. The loop will feel a torque as it's in the magnetic field, which will cause it to spin. And then if we can harness that energy of the spinning in order to do some work, then we have a motor. So generators and motors are sort of using the same setup, but they're using it in a different way. The generator uses external force to generate electricity. A motor will use electricity to generate some sort of external force. So I wanted to make sure that you at least thought about that material. Like I said, I don't know that we'll have time to talk about it in class, but hopefully you find this somewhat enlightening or interesting to learn a little bit more about it and another application of Faraday's law.